I see it.
Okay,
Okay.
perfect. There we go.
Okay.
Yeah.
All right. So let me share my screen. Okay. Okay. So this is, you know, a few years back before I wrote that paper that we talked about, Daniel and Joe. I put together this blog, and the blog was just kind of like I did it like as my mind was trying to piece stuff together. I wouldn't characterize this as like a high standard of rigor, what's in here, but it's but more like a brain dump of the different things I was thinking about. But some of it is pretty good, and I think what we covered today will be quite interesting. So one of the things I started thinking about was this question of free will, and how can you have free will and also the laws of physics at the same time? And you know, it's certainly possible that our conscious mind sits outside of the physical, of what physics describes. But then you have the question of, like, when you make choices, how does your mind then influence the physics or change the physics? Like, there's a Greek philosopher, I want to say it was Democritus or something like that. And he talked about causing your mind can cause the atoms to swerve. You know, they have a normal path they would go on if they followed physical law, but your mind, when you make a choice, however that happens, you can cause the atoms to swerve, and that's how minds intervene in the physical world. But otherwise, the world follows physical law. So, well, that's possible. I want to kind of say, let's punt on that idea. It's possible, but if we can understand the universe within just the laws of physics, and we can marry subjective experience and the mind and consciousness together with physics without having anything outside of the laws of physics, then that's in some sense a simpler theory than if we have two separate things going on. And so I want to just, in this conversation, we'll pursue that and see how far we can get and see what we can explain.
Right.
If the philosophers refer to laws of physics as the causal closure of physics. Like, and what I mean by that is, you know, like when you studied planetary systems, let's say, like back in high school or whatever, you know, like you have a gravitational mass and some planets going around. Once you put them in motion, you can calculate where the Earth or where Jupiter will be at any point in the future. Like, it's all deterministic. Thousands of years in the future, you can calculate with Newton's equations, you know, planet goes around, you know, right where it'll be. And electromagnetism, which is the other primary force that affects our lives, works similarly. It's it works kind of like gravitation. You have positive and negative charges. That's different, but still it's a force that's inversely proportional to the distance between the two things. But there's nothing uncertain about it. It's, the trajectory of macroscopic objects is very precisely predictable. Now, when you go down and look at the universe at really small levels, like on the scale of atoms, quantum mechanics comes into play, and quantum mechanics ends it introduces chance or probability into the universe. But a lot of physicists and most biologists at this point want to take the view that the quantum mechanics effects are there, but once you get to the scale of things that matter for biology, it's more or less the world's deterministic. Like the quantum effects they're there, but they average out. Like, and so for all practical purposes in the mind, you have chemical reactions taking place, and the chemical reactions are basically deterministic. And so then we're left with a problem. If everything that comprises my body is deterministic, it's what I do in the next second, 2 seconds, 5 seconds, 10 seconds, it's predetermined. You just have to calculate these chemical reactions. You could simulate on a computer, and then everything I do is predetermined. I have no real free will. But I feel like it. I feel like I'm making a choice. I feel like I'm making choices in these words I'm saying. So the physical description is at least at odds with the subjective characteristics of how I feel. So, you know, now most physicists, a lot certainly, and stuff, and a lot of psychologists, all that stuff, I know, you know, come in from the standpoint, okay, it's just an illusion. You feel like you have choice, but you don't really. And when they kind of hang their hat on some experiments, you know, done in the early 80s by Libet, Libet, who put some electrodes in people's brains and took some measurements, and he showed that he could predict, you know, which choice they would make, you know, with a pretty fair degree of accuracy, like in a like a laboratory setting and that kind of stuff. And so obviously people that want to believe, you know, that in the laws of in the physical world and that there's no free will, they jump all over that, right? And it's like it was like, yeah, it's proof, it's proven, the feeling of choice, and it's all illusion. Well, since those experiments of Libet, you know, others have come out and showed that actually, you know, people can outwit the machine. You can try and predict them, but, you know, if people are trying to avoid prediction, they can do it. And so those experiments, while they're not like totally discarded, there is some evidence that there's more going on than just what Libet was measuring with his electrodes, which are essentially electrical impulses and stuff. All right, so then we have a problem though. All right, so let's say, so everything at the classical level, big level, is sort of deterministic, but I feel like I have choice. So how could that possibly be? So let's jump into this. So let's talk about, so this is, and Joe, you'll remember you were talking about your quantum mechanics class. You'll maybe remember this. So this guy right here, this right here is an apparatus called a Stern-Gerlach apparatus. What they did is they had silver atoms. Silver atoms come out of, I don't know what this is, like a furnace or something like that. And the silver atoms come out, and the silver atoms have a spin to them, just like an electron has a spin. And that spin can either be up or it can be down. This is where quantum kicks in. So it can only be one of these two things. It can't point in this direction. Well, let me elaborate a little bit more before we go into that. So it goes through, the silver atom comes firing out of here. It goes through this magnetic field, and then it's projected onto this like photographic plate, whatever this is, and it'll either go to this dot or it goes down here to this dot. It doesn't go anywhere in between. There's nothing in here, nothing off to the sides. It always goes to one dot or the other. So the silver atom is either spin up or spin down. Now if you put, now just to recap some quantum jargon, if we put, let's say a silver atom came through and it took this trajectory, the top trajectory. If we put another north-south magnet here, aligned the same way as this one, then we'd get the same answer. Like if it went to this one, then it would still be spin up when we measured again. That's called, the atom is in an eigenstate. This is a measurement. This is a measurement device. It basically is an operator in the language of quantum mechanics. And the silver atom is in an eigenstate of that operator, and it will stay there until it interacts with other things. It will stay in an eigenstate. If we took another magnet and turned it on its side so that north was coming out of the page, then that atom would be split 50-50 again. It would either be found to be pointing out of the page or into the page. And there's no way to predict which. And it would do it with each one with 50% chance. And then the silver atom is an eigenstate of this new measurement operator, a magnet pointing in this direction, out of the page. So that's kind of encapsulates the basic nature of quantum mechanics and the probabilities. It doesn't talk about entanglement. We'll skip that for the moment, but that covers, you know, how the gist of quantum mechanics. It's probabilistic in nature. There's no hidden variables. That's known. There's no way to predict it. That was proven. To a very high degree, the quantum mechanics math works. You can measure it to several decimal places of precision, and the theory seems to be very, very solid. It is extremely hard to work out the quantum mechanics, though, of many body systems. So this is a silver magnet, and one silver atom goes through at a time, and it's easy to calculate what happens then. But when you get into on the scale of things like a protein molecule or the types of molecules that you have in the body, it's like you can spend a few months on a supercomputer just to simulate a simple protein for a millisecond. Mm-hmm. It's crazy how complex the physics gets. So it's almost impossible to simulate, although in principle possible, practically impossible to simulate something on the scale of a human or a mind. Okay, but nonetheless, this graph or this experiment tells us how probability enters the universe in the world of physics. What I want to say to you guys is I think this is how choice also enters the universe. I want to say that, so we've talked before and we've said, hey, I think the characteristics of the mind are similar. Some characteristics of mind have similarities to superfluid physical systems. Like the physics of superfluids parallels various aspects of subjective experience. One aspect of subjective experience, of course, we talked about is choice. So I think choice, the way it comes into play is choice and your preferences are dual to quantum probabilities. So what do I mean by that? When we put the silver atom through this thing, we can objectively calculate what probabilities it will do this and what probabilities it will do this. In this case, if it's 50-50 probability, this silver atom has some proto experience, the basic building blocks of subjective experience. It makes a basic choice, like it feels in some very elementary way a preference for being spin up and an equal preference for being spin down. Now, I'm not coming here to tell you that this is like a choice that we make in the sense that it's aware that it's making a choice. It's not. Or anything like high level that's close to what we're used to thinking of. But it's the most basic element of if you can imagine, of how choice enters the universe. So in every quantum system, including superfluids and superconductors, anytime a quantum measurement is made, anytime any aspect of that system is measured, by something in the environment, something around it, that's equivalent to that system making a choice. So let me just do a little experiment or a little thing on you guys. So just think about the choice. Like, let's say you have a choice right now to have ice cream, and there's, let's call it, two choices, vanilla and chocolate. Just think in your mind, and you guys can tell me which would you pick.
I would pick chocolate.
Vanilla.
Chocolate, okay, vanilla. Okay, let me ask you that question one more time. Just same question. You get to choose again. Which would you choose right now?
Probably the same thing.
Yeah. How about you? Okay. So what I'm saying I just did is we just took we took a measurement of some aspect of your mind. Joe took vanilla, the upper path. Daniel took chocolate, or I'm sorry, I got that backwards.
Yeah.
But you get the idea. One of you chose this path and the other chose this path. And then when we asked again, you were in an eigenstate of, call it the ice cream operator, the ice cream choice operator. You choose chocolate again, you choose vanilla again. You're in an eigenstate of that operator. And so that's where I think basic choice enters into the mind. Your choices, your preferences, whatever they be, about whatever you would think of, to go out for a run, to go to Hawaii, Daniel. All those things are dual to quantum probabilities. And then your mind has a way of subjecting itself to measurement and interacts with a lot of stuff in your brain. And we'll get to that in 1 second. But you can, this is the basics of choice. And you can see here, I won't go into too much on this, but this was just a binary system where there's two things, vanilla or chocolate. But you can, the same stuff applies when there's many, many choices. You know, like this is a system where there's, like, call it 3 particles entangled together. There's 3 individual spin states, so they can have a whole spectrum of different spins. And so when you put them through the measuring apparatus, you could have 4 outcomes or 100 outcomes or 1,000,000 outcomes. But whatever the case, it's just like in life, there might be binary choices. There might be choices where you have 10 million flavors of ice cream to choose from, or whatever it may be. But it's a quantum measurement is equivalent to making a choice. And the probabilities that a physicist would calculate, if they hypothetically could model your mind, the probabilities they calculate for each outcome would be dual to the preference you feel for that choice. So like if you strongly preferred chocolate, your quantum probability would be 95% chocolate, 5% vanilla, maybe 99%. You guys can feel what your probabilities felt like. What it feels like to you is the same as the probability in that quantum wave function.
Mm-hmm.
So let's see, what more? There was another key thing to say about that. Okay, so there's a field called quantum cognition. And it's a field, it's where psychology meets quantum mechanics. And the people that are in that field are very careful not to suggest that quantum mechanics is taking place in the mind, because that kind of is taboo, right? And people won't listen to them if they throw that out there. But what they do is they quietly go about and say, you know, we just sort of noticed that a lot of things about psychological studies mirrors quantum mechanics. It mirrors the mathematics of quantum mechanics. Not saying it is quantum mechanics, but it mirrors the mathematics. And one example of that is the order in which you ask questions. So if you ask people 3 questions and you ask them A, B, C, you will get a different answer if you ask them B, A, C or C, B, A. The order of questions matters, and that's proven in psychological studies. That is also the characteristic general nature of quantum mechanics. If we put this this silver atom through a magnet that's aligned vertically first, and then we measure it again vertically, you know, like the order matters. If we go vertically, horizontally, then it will go through the first measurement. This measurement, then it'll be either pointing up or down. When it goes through this one, it won't change it. It's an eigenstate of that one. And then when it goes through this measurement, pointing out of the page, it'll split 50-50 and be aligned either out of the page or into the page. But if we move, instead of doing this measurement here, we put it in the middle, then this measurement happens as before. You know, the silver atom would be pointing up or down 50-50. This one out of the page would split it again 50-50 to in the page, out of the page. And then this measuring it up or down again would split it again 50-50 and put it back into an eigenstate of this direction, up or down. So like in general, the order that you measure things matters in quantum mechanics. And you can go further than that. You can Google quantum cognition and question order. I think will get you a lot of research on this topic. There have been some good papers published. And the mathematics, that, like if you model humans as quantum systems, then you can accurately model the choices that they'll make. I'm not saying predict them, but like the quantum system will predict that, hey, order will matter, and some character, and in a mathematical way, how much does order matter? And when you observe that in psychological systems, in people, in trials, they seem to follow that same sort of mathematics. There are a couple other things that are in quantum cognition where there are parallels too. So there's some interesting parallels, things like quantum choice and between personal choice and quantum mechanics. Now that field gets, they're very careful, like I said, and I feel like that field has now been taken over by machine learning. So there's not a lot of grant money to do quantum research about brains, I don't think, anymore. Folks are much more interested in spending money on using machine learning, which is it's a totally classical process to study brains, which is essentially saying you're treating the brain as these are chemical reactions taking place, and there's nothing quantum about them. Right. Joe and I both do machine learning, so I'm not against machine learning. I love it. It's my passion, but it's my passion because I'm trying to understand where intelligence comes from, human intelligence of living things. So, and we'll talk about that another day. Machine learning does great stuff, amazing stuff. It approximates a lot of the great things that people do. Like you can teach a computer to recognize cats, dogs, all that kind of stuff. But it comes up short on a lot of metrics too. And I think, well, as we get into this more and more, I think you'll see that in the physics of these superfluids and things like that, you can close that gap and understand what the differences are between a machine simulating a deep learning neural network and a biological system, which uses a similar, at the neurological level, a similar structure, but it's different in a very important way. And we'll talk about that later. But anyway, the point here, this is the basic, I think, the basic way that choice and essentially free will enters the universe. You do have true choice in this universe. Your choices aren't predicted. It's not possible to predict them. It may be possible to predict what you choose probabilistically. Like I could have said, Joe will pick chocolate 99% of the time. I know her, that kind of thing. But to me, that's not sacrificing free will. That might just be knowing someone to know their preferences, but they still can make that choice, and nothing, if it's truly quantum, then nothing can predict exactly what they're going to choose. Just you can predict the probability distribution.
Right.
Okay. Now that's a basic choice. So like choosing ice cream and that kind of stuff. Let's move on to focusing of attention and that kind of stuff. I mean, because you guys both do more than just make choices. You're not served up choices throughout your day. You can decide what to think about. You can decide what choices to make. We could decide to talk about ice cream or not ever even talk about that. So then you're never measured in the ice cream basis, as there were. Okay, so where's this next one?
That reminds me of something. I think I can't remember if it was Hindu or some other Eastern philosophy. It was Eastern, definitely, but it was talking about attention and how attention is a form of love. Have you guys heard any kind of analogy like that? That it's, to me, it just rings true. I can't even explain it, but it feels right.
Mm-hmm. Yeah, I think that's a very interesting connection there.
Yeah, but yeah, go ahead, Mike.
Okay, so now remember the last time we were talking about Stern-Gerlach experiment. The magnet itself was not a quantum device. We had a macroscopic, magnet sitting here. This was a magnet, and but now let's say we have some kind of, instead of a magnet, a macroscopic device, we now have some sort of quantum system. I don't know. I drew this as a bunch of entangled particles, and they're interacting with each other. Maybe this is something analogous to the physics of superfluid, because in like a superfluid, or like in the way that you get superfluidity into the body, or one proposal for that is called a Froelich condensate. And so a Froelich condensate or superfluid or superconductor is ripe with extensive quantum entanglement. And so that might be a kind of physical system that would employ this sort of entanglement that I'm trying to illustrate here. And the idea is that, let's say you had a whole string of entangled particles. Before we were talking about silver atoms, so let's just suppose these are silver atoms, but now there's a whole bunch of silver atoms and they all have spins, so they create a magnetic field where this is, north and this point south, and the silver atoms go through. The silver atoms are entangled with all these others. So you have, like, let's call it a million silver atoms here, a million silver atoms down here, and they're all spin is a line pointing up. So they create this magnetic field. So, but they're also entangled with this silver atom that's going through the apparatus. Okay. So now the superfluid itself, when these things are all entangled together, it's as if the physical system behaves as if it's one thing. Like, there's no way to break it down into its parts, component parts, when something's entangled. It's like Lenny Susskind's got a great slogan for this. It's like you can know everything there is to know about the physical system, but you won't know anything about its parts. Like, I mean, and I'm not saying that's just for lack of trying. The knowledge about its parts ceases to exist. The knowledge about its parts ceases to exist unless you break that superfluid apart, or you break that substance apart. It's like they truly become one thing.
Right.
And so I think a way to an analogy at the human level that loosely describes is, imagine you have two jump ropes, right? Two separate things. Now you see the kids on the playground and they're playing that jump rope game, like double dutch. There's now two jump ropes have become one double dutch system, and they rotate together and they're synchronized and that kind of stuff. That's loosely like a quantum system. You in some
becoming
way,
entangled.
Becoming entangled. You entangle things together, they become one system. So all these particles here are entangled together and they become one system. So now you can imagine there's two choices taking place. One might be that all these particles can choose to be aligned, pointing up, in which case they become like a Stern-Gerlach apparatus. They create this magnetic field here. Or they can choose to be some up, some down, so the spins, the magnetic fields cancel each other out, and then there's no magnetic field. And then, but the subjective parallel of that is, if they choose to be all aligned up or down, that's making a choice. That's choosing to think about, say, ice cream. If you choose all the spins aligned, you're going to make a measurement of yourself, and you're going to choose to think about ice cream. And then when the other part of you goes through the apparatus, you pick chocolate or you pick vanilla. So by having a nested system like this, where there's, say, two connected quantum measurements, there's two choices that are connected. And so this, what I'm trying to get at is, this is the basics of focusing your attention and then how you make a choice. So in your mind, which I'm saying is just like a superfluid, there's some quantum system. Maybe it's alignment of magnetic spins, but it could be many, many different things. That's just one possible example. But maybe several parts of you choose to align and create a magnetic field, which means, based on where it is in the brain that's occurring, means you're thinking about ice cream. And then from there, you're going to think about making ice cream and make a choice about ice cream. And then the next part is, when this part of you is measured, you actually make that choice. That's what happens when you pick ice cream, you pick vanilla, and then after that, you're in the eigenstate of this operator. But you've chosen to create that operator by choosing, it's a nested quantum choice. Does that make sense? So wherever you focus your attention, I'm saying that's focusing attention is itself a choice of what you're going to think about. you know, and then if what you're thinking about involves making a choice, like ice cream, that's a nested or a second choice, but a choice that's made possible because you were thinking about ice cream in the first place, or something provoked you to think about ice cream. So I think
Could
a
that
lot
be
of the
related?
physics.
Oh,
Yeah, go ahead,
go ahead.
Joe.
I was just gonna say, could that be related to manifestation as well? Like the idea of manifestation. So you keep thinking about that choice, right? And then once it's time to like go through that spectrum where you make the decision, since you just like, for example, I was thinking about chocolate. You know, chocolate's like, that's the first thought that came to my mind, and it was in my head, and I said chocolate. So if we want something in our life, and we keep just thinking about it, and then just like stay focused on that one dart, and would that be our choice? Would that be ended up happening? So is that idea sort of related or no?
I think you're doing exactly what's going on in this system right there.
Yeah,
You're describing exactly this. It's you know, yeah, that's exactly what I'm saying. Those choices, those are all quantum, like the equivalent of quantum measurements. Now, yeah, and you hit the nail on the head. I think one problem we have is, you know, I talk about staying in an eigenstate, and one challenge we'll face is quantum systems are notorious for decoherence. And so that means you measure them. Let's say you go through that Stern-Gerlach and you measure it and it's spin up. Once that silver atom interacts with the environment, it goes through decoherence. And so it's no longer in an eigenstate. And that happens really fast. That tends to happen on like in biological systems, people have calculated that will happen on picosecond timescales. Like if you had some quantum states, so that means, you know, there's no way you could remember if being in an eigenstate was the only way you remembered your choice, that wouldn't work. At least if it was just some kind of, like in the traditional way of thinking of entanglement, the things decohere too fast. But a picosecond is what, like a thousandth of a nanosecond. So that's a trillionth of a second, I think. Yeah. So really, really fast.
Can't even imagine.
Really, yeah. But with the system that is kind of like a superfluid, the Froehlich condensate, things can stay entangled longer there because energy is being pumped, constantly being pumped into the system. So the Froehlich condensate can exist longer. And there have been some experimental studies now where they've zapped a protein, biological protein, with a terahertz laser, and they can get a Froehlich condensate to form, and it lasts on the order of milliseconds. So, I mean, that's much, much longer. That's still short, but it's much, much longer than picoseconds. And I think they're onto something there. Like, imagine the laser kept zapping, something like a metabolism, kept pumping energy into that system, then the Froehlich condensate would be sustained. Now, if even in that case, the decoherence of the condensate happens in millisecond timescales, but metabolism, energy transfer happens much faster than that. Like molecules in your body are vibrating really, really fast. Like DNA vibrates on femtosecond timescales, 1,000 times faster than picosecond. That means that DNA or other biomolecules could be emitting terahertz radiation and pumping energy into the system on timescales that are much shorter than the decoherence time. And that's what you need to sustain something in a quantum state, to sustain like, you know, a Froehlich condensate in the body. So anyway, I mean, to sum it up though, I think Froehlich condensate opens the door to the possibility that this sort of system exists in a warm, wet biological environment. I think that's on the table, that we've observed a Froehlich condensate in a laboratory, albeit under a terahertz laser, is starting to connect the dots, that this sort of physics could be present in a biological system. And so then, as we talked about, some of the physical, the way you describe it quantum mechanically and with physics equations, sort of mirrors, you know, pretty well the characteristics of this important aspect of consciousness, choice and focusing of attention.
You know, I've been seeing various websites and studies talking about biological systems having quantum mechanical properties, you know, like specifically the first one that comes to mind is photosynthesis in plants. Have you guys seen this?
Yeah.
You know, they're in the, you know, it's multiple things, and they're even, you know, they're finding that they can, you know, get large molecules quantumly entangled. They can, I think they even quantumly entangled tardigrade. You know, a full-sized animal.
Oh, really?
Yeah.
What was it? What is it? What animal was it?
It's a tardigrade, a water bear.
Oh, I know what that is.
Yeah. So that's hilarious. That's fun. First, it's funny, and second of all, it's quite it flies in the face of this idea that quantum mechanics, like you said, is completely only this very microscopic thing. It has no real world effects at this macroscopic level. But something that I just wanted to hammer in real quick is this idea of, like, you know, of microscopic level versus the macroscopic level of reality. And, you know, microscopic is quantum, or you know what I mean by microscopic, and then the macroscopic world is what we actually deal with, is actual reality. And to me, the macroscopic world is perception. You know, it's quantum mechanical until it enters perception, and then perception is totally just, I have no basis for believing this whatsoever. But, you know, that the macroscopic world is something that we literally create, right, in our minds. You know, you know, and then even at the global scale, you know, ADS CFT correspondence and all that stuff. I don't even know how to connect the dots there, but
no, absolutely. There's no doubt in my mind. We'll talk about this. We can get back to this another time, but because it's a subject unto itself. But there's no doubt that in my mind that that reality that we're perceiving is a creation of the mind. It doesn't independently exist.
Right.
It's a creation of the mind, and the physics that's dual to that. What's its mirror image is the geometry of space-time inside your body. This Freudly condensate, because it's what's called, you know, a strongly coupled system. It's highly entangled. Every single particle strongly affects every other particle. Becomes like a superfluid or condensate, and so it's going to distort the geometry of space-time itself. The space you're in right now is being shaped by all that information that's coming to your senses, be it your eyes, your ears, everything you're perceiving. What's on your mind right now is shaping the geometry of space-time itself inside your body, probably subtly, in very subtle ways, but not in simple ways at all. Like it's taking complex information and it's finding the simplest description of that information. And that simplest description of that information sorts out that information into concepts, but it also comes up with one unified description, just like your brain's doing with grandmother neurons, you know, with all the conceptual things that are firing in your brain. Space-time's doing that same sort of stuff. And so I think space-time is the background that shapes the neurological structure of the brain. In machine learning, when we train a deep learning model, we train it with back propagation. It's a very simple way, in terms of mathematics, it's a very simple way of training a neural network. And as a result, we get neural networks that are good at things, but they're very, very prone to mistakes if you change the circumstances. For example, machine can be great at recognizing cats, can get it 99.5% of the time correct when you look at images on Facebook. But if you put a little watermark over the cat, you know, like a little watermark, it starts to mess up, and it thinks the cat's a couch or something. It just makes it really, really bad with just a simple little watermark. Where you would look at it and you would hardly notice the watermark. You just go, oh, that's nothing.
Right.
Yeah. So the difference there is we're training things with this thing called back propagation. The brain has a much better way of training itself. It's learning from space-time itself. Space-time is a much more powerful computer than any classical process like what we do with backpropagation. Backpropagation can be done in computer machines, but what space-time is doing is a much harder problem. It's solving a complexity problem, which a computer cannot solve, at least efficiently is the proper term for it, but basically means you cannot solve it, like in the age of the universe. And we're doing it real time. So the space-time geometry is maybe through some sort of interference or something, but it's providing shape to the neurons, and they're filling in the, not the cavities, but the depressions or whatever, the points in space-time of curvature. So your neurons are filling in, are mirroring the structure of space-time. And so if you wanted to train a brain, you wouldn't do it with backpropagation. You'd make a superfluid type system, a Fourier condensate, and let the neurons mirror the geometry of that space-time sorts out. That would be much, much more effective if it was possible. And that's what life does, I think.
The neuron connections?
Yes.
The connections between the neurons would mirror the actual three-dimensional.
Yes. Yeah. So if you looked at a map, of neurons, that's going to mirror the geometry of space-time. So let's go. Let me see if I have a picture of that on this blog. Or well, like I think one way to think of it is, have you ever looked up at the stars at night and you think, oh, that looks kind of like neurons, like it looks like you're looking at the brain.
Yeah,
that's not by accident. That's not by
the galaxy at the largest structure, right? Have you seen those pictures? Exactly like how you're saying. Right.
So yeah, that's on small scales. In the brain, that geometry is, I think, driving the geometrical structure of, here, let me share my screen here and make this point in the paper. Just so you have some intuition to it, visual it. So here, this picture right here is neurons. This is an example of the geometry of space-time in the ADS-CFT correspondence. But and this is kind of an example of a neural network. So this artificial one, and how we think of it in computers. But this is saying this structure here. This is like mirroring the space-time geometry. If you were to fit this geometry with like tiles, you tile it just like this. These neurons are filling in. Space-time is the heavy lifter for learning and living things. Space-time is doing the heavy lifting, not the neurons. The neurons are giving you memory, because space-time those thoughts won't persist more than a fraction of a second. So you would have no way, without neurons, you have no way of remembering what happened 1 second ago. So nothing can persist, but you have, like a baby, you can perceive the world, but you can't remember it at all. And this neural structure fills in and gives you a way to remember things. And it fills in not by backpropagation, which is another term is gradient descent. It's not doing that. It's filling in the geometry. It's mirroring the geometry that space-time is solving real time as you experience things. So like the geometry inside your brain might actually look like, some kind of holographic image of what you're seeing. What you're experiencing right now is encoded in this hologram in your brain, in this complex geometry with many local surfaces, many bumps and wiggles and all that stuff. This is Einstein. This is space-time geometry. And how does all that fit together with Einstein? Einstein, what he came up with was an approximation of how space-time works. He said, it's mass, or more precisely energy, that curves space-time, that causes it to shape itself, that distorts it. What we're learning with ADS-CFT is that's an approximation. That's approximately true, but more precisely, it's quantum information. It's information that shapes space-time, not mass, not energy. In the classical limit, it's mass and energy, But if you look up really close, or if you look at complex entangled systems like superfluids, it's quantum information that shapes space-time. Space-time is sorting out the simplest description of that information. That's what this is. This neurological structure is doing the same thing. It's just mirroring space-time. So your baby is perceiving the world, but it can't persist that perception for more than milliseconds. So it can't track objects, but a baby does have basic recognition, like even before the neurological structures can form. There's evidence that they can recognize their father, their mother, that kind of stuff. They just can't, it's just like you just imagine yourself being ultimately in the moment. You have no way to not be in the moment. Like you're just experiencing things, but you can't do anything about it because you can't remember anything from 1 second ago. So you're just experiencing the world. You can't retain anything. That's where neurons come in, I think. And then that gives you a way of where like the very small things that don't have neurological structures can still have perceptions and still sort of do complex and intelligent things, like things like viruses. Viruses are, probably having basic level perceptions,
single-celled organisms.
Single-celled organisms, right.
Plants.
They're having perceptions, plants, all these things without neurons. They still they're still experiencing it, just as space-time is there. They're distorting space-time too. They're having experiences, but they don't have the complex neural structure to retain memories and persist thoughts. So that's sort of the idea.
That's interesting.
Before neurons, there were RNA and DNA, I think, do the same sort of thing. That's a way of persisting thought or persisting experience, like encoding that to persist through time. I think RNA and DNA were discovered as a mathematical solution by living things as a way to store information. So in other words, life started with the creation of a basic superfluid, just like when we do it in the lab, like superfluid helium. Bang, that's the first life form. And just the way that then superfluid helium adapts to stress, if you heat it, it adapts to that stress. That superfluid, which was created for just a moment on this earth, adapts, and it quickly invents a metabolism to sustain itself. It invents that, and it quickly also invents a way to store its experiences, like where is the food or whatever it needs to remember. And it encodes memories in the RNA. So those are two early inventions, probably that happened in the first second of existence of the superfluid state, because it needs to, just like superfluid, if it's heated, it will fall apart. This living superfluid will die. And so it needs to adapt to that stress very quickly. Has to create something to derive a metabolism, and it needs some way to retain memories. Bang, like that. It solves both in a fraction of a second, and that's the beginning of life. So the chicken and the egg happen at the same time. The chicken and the egg happen at the exact same time. In biological terms, DNA and metabolism, they come basically at the same time. And why it looks like life is created, like it looks like intelligent design. The intelligence is right here in space-time itself. Space-time is solving a complexity problem, and that is a capability. That's what you're doing. You're doing it right now just by perceiving. But that's a power which is, if you were building a computer system that could adapt to its environment, and you've got one wish, like one sort of oracle, you'd want to have an oracle that could solve complexity problems for you, because that means you can. So finding the simplest description of stuff means you understand it. That's what goes on when you understand something, right? You're breaking it down to its components, parts, and figuring out how it works. Space-time is doing that, and that's what you need to do: just adapt and survive as a living thing. So, anyway, there's an enormous number of parallels: perception, choice, focused attention, and then evolutionary parallels with like what superfluids are doing and what living things are doing. So with all that said, I know we went really fast there and stuff. So we can switch topics, or we could go back over any of that stuff, or if there's any questions, or you guys want to think about it from a different angle.
My phone is dying real quick, and there's some questions I wanted to ask real quick. So,
okay,
do you guys want to have some kind of platform or some kind of something we can dump articles we find interesting? Because I want to, you know, it's almost too much to talk about in such a short period of time. I have almost nobody I'm talking to about this kind of stuff at this level of detail. So is there any kind of what works best for you guys? Because you guys are already collaborating, like you said, at work, I think. So what do you guys, Discord, some kind of, you know, Dropbox, like what's a good platform?
I'm open to any of those things. I'm not high tech savvy for that kind of stuff, so you guys can pick what works. But I think we can start by putting this video recording in there, and then drop other stuff, and we can repeat this and gather our thoughts, because I think other people will be interested too.
Yeah, definitely. Whatever works the best. Discord, Slack. I'm using everything at this point.
Okay, I have a Discord.
Yeah. I can go ahead and put together like a Discord group for us, and then have it sent to you guys, and then we could just have that our sandbox to play with.
Good.
Yeah.
So what was some of the first stuff that came to your mind watching Mike's presentation?
Like I said, a lot of this stuff like generally has been talked about in the classes I've taken before, but not to this depth, of course, because nobody's got time to explain, you know, their views in such a detailed manner. But it's really interesting to see how there's like so many things, they're like aligning at the same time, and they're functioning all together, but we're just not aware of them. And even though like we have the resource to look for and then to make the connections, but it's like at a micro level, there's like so many connections to make, you know. It's kind of like a string theory, like you have like it's connecting to so many things at so many times. So and that's I love hearing about it, and it's just so much good information today. And yeah, I'm really intrigued, and I'm looking forward to what we have in store next. Because this was really good, and I feel like it was really like educative, and at the same time, a lot of my questions in my mind were answered in a lot of ways. So not I wouldn't say like not completely, but some parts of it has been start to like fill up and stuff like that. So yeah. And like, and I think Mike mentioned in the presentation when he was talking about it, that in the beginning he said that religion and like physics are not on the different spectrum; they're both the same. As a person who used to think that it's opposite, I totally agree to it. Because when I went into the major, I was completely like, religion is different, but it has to work through with the laws of physics. But then when I kind of transformed, I was more of like, no, they go hand in hand. So
two sides of the same coin kind of thing.
Yeah, it's kind of like this, kind of like that. So yeah, and I'm looking forward to what we have in store next, like I said, and it was really nice to have this much intellect. I would rather do this than university, because this is more educational than sitting in the classes. And then, you know, that's what professors do. They leave the information there. It's up to you if you want to go into depth. They'll just introduce the idea of it, but never go in. And I'm a type of person who learns like by more of like a visual learner, you know. You can't just put the words in my mind. I need to see graphs, drawings, and everything. So that's how like stuff makes sense in my head. So it was really helpful. No, I'm really glad you invited me. It was really great.
Let's do another session sometime when it works for you guys about let's talk about evolution, because science has some real problems there, like where some of the foundational theories like natural selection are almost dogmatic in nature. They're just accepted without verification. And we have a totally different approach that doesn't require Well, it addresses a lot of the problems with the theory of natural selection. We have our challenges to show for sure. Like, how could you get a superfluid to exist on its own?
Yeah.
Millisecond, how could that happen? Sure, that's true. But given that, we can show how things can adapt to stress. Let's talk about that another time, because we're in a position to address evolution from a much better perspective if we can get this superfluid state to exist, which might very well be the case with the Fourier condensate. I'm gonna stop the recording right now.
Sure.
It's something I've been talking about.